on page 25, Blue Book. 25, 25. Okay, so hopefully by this point, you have gotten the idea of stoichiometry. What is step one of any stoichiometry problem? Find the moles of A. Step two is find moles of B. Okay, and then everything else is just using mole conversion factors. Today, we're going to look at the particle ratio, which adds in an extra little thing, because the mole ratio is the same as the particle ratio. And if you want to, sometimes you can use that to make your life easier. You can make it go faster. Or you can just be like, I'm always going to convert to moles of A and then moles of B, and you'll never go wrong, really. Okay. So, mole ratio, this is from the coefficients. Particle ratio, that's from the coefficients, page 25, if anyone's wondering. And of course, Avogadro's number. Remember, I do not want to see 6.02 times 10 to the 23 moles. That would be a very, very bad thing, okay? So here we have our mole chart. The mole ratio and the particle ratio are the same. So if I was to give you the number of particles of A, if I gave you this, if this was your given, and I asked you to find the moles of B, that's what you want, you could actually take two pathways, yes? You could find moles of A and then moles of B. I would probably recommend that because it follows the pattern that you're used to. Find moles of A and find moles of B. But if you don't want to do that, you could find the number of particles of B and then find the moles of B. So there's two directions you could take. Up to you which one you use. Okay? So, mole ratio, just showing that they're the same. If you have a 3 to 2 coefficient ratio, you have 3 moles of H2 to 2 moles of NH3, or you can say I have 3 H2 molecules for every 2 H2 molecules. Alrighty, here we go. We have a reaction here. We are burning, some propane. How many carbon dioxide molecules are produced when 0.76 moles of propane are combusted? So we are starting with moles of propane, which is C3H8. And we want to finish with the number of CO2 molecules. So we are starting here with the moles of C3H8, and we want to finish with the number of particles. So we actually don't need to find moles of A because we are given moles of A. Yes? So we could draw a little map for this. We could say we want to go from moles of A to moles of B, which is the CO2, to the number of molecules of CO2. Would that be an easy enough calculation? I hope so. So we don't know how many molecules of CO2, we are starting with 0.76 moles C3H8. We want to convert to moles of CO2 from moles of C3H8. Where do those numbers come from? The coefficients. So we go back to our reaction and we say there is 1 C3H8 for every 3 CO2, 1 C3H8 for every 3 CO2, and then finally we need to do a second step because we have found moles of CO2, but we don't want moles, we want molecules. So we need to put moles of CO2 on the bottom and molecules of CO2 on the top. I'd like you to tell your partner what numbers go on the top and the bottom of that conversion factor. What numbers go on the top and the bottom of that conversion factor? I like that. Avogadro over 1, yes. 6.02 times 10 to the 23 molecules per 1 mole, because the 1 goes with the mole, yes. All right, we do our math and we get, I'm going to cheat because I believe the math is down here. Yes, it is. Okay, so there's our same calculation that we just did. We get 1.4 times 10 to the 24 CO2 molecules. Now, it is possible to take a different route. If we are starting here and finishing here, what's the other route we could take? We could go particles of A. Okay, so let's take a look at what that looks like. We can go from moles of C3H8 to molecules of C3H8. So 0.76 moles of C3H8. We want to convert to molecules of C3H8. What numbers go on the top and the bottom of that conversion factor? The 1 goes with the mole, and Avogadro goes with the molecule. 6.02 times 10 to the 23. And then you can say, I'm going to use the particle ratio. There is, from our balanced equation, there's 1 C3H8 for every 3 CO2. So 1 C3H8 for every 3, whoops, wrong way around, 3 CO2 molecules for every 1 C3H8 molecule. And if you look at this calculation, in both cases we are multiplying by 6.02 times 10 to the 23, and we're multiplying by 3 over 1. It's just the order in which we do so that has swapped. Is good? Okay, cool. How many moles are required to produce 4.8 times 10 to the 24 NH3 molecules? So you would be going from molecules, here's where we're starting, molecules to moles. So 4.8 times 10 to the 23, oh, pen battery low, okay. NH3 molecules, and we want to find moles, convert to moles of A, right? 1 mole of NH3 for every, what number and unit are going to go on the bottom? Tell your partner there. What number and unit on the bottom? Hopefully 6.02 times 10 to the 23 NH3. So we've found moles of A, and now we're going to find moles of B, which in this case is calcium hydroxide. So we're going to cancel the moles of NH3 and find the moles of CaOH2. And our coefficients, because whenever we go from moles of one thing to moles of another thing, we go find our coefficients. 2 NH3 for every 1 CaOH2, 2 NH3 for every 1 CaOH2, and there's our lovely math, and there's our lovely answer. That did die. Okay. Is good? Could you do a different route to get from the number of particles of NH3 where's my erase button? There's my erase button. How else could I get from here to my finish line? I could go from number of particles of A to number of particles of B to number of moles of B. Do you want to see that calculation? Anyone? No, okay. It's there if you want it. Now, here is a complete chart for stoichiometry. I actually have a copy of this for you. You also have I don't know what I've done with it, but I have one of these for you, so I'll get that out to you. First step, always convert to moles, and it shows you if I start with grams, I'm going to use the molar mass. If I start with particles, I'm going to use Avogadro's number. If I start with a gas, volume of a gas, I'm going to use 22.4 liters per mole. If I start with volume of a solution, I will use molarity. And if I start with volume of solid, liquid, or gas, not at STP, I will use density. And you can use those same conversion factors to convert out of moles at the end. However, there's one thing that's different over here. If you're finishing, and this is what you did over the weekend, I hope, is if you're finding concentration, remember, what is concentration measured in? Molarity, which is moles over liters. So are you going to convert there? No, you are going to divide by liters to find the concentration. Okay? I don't think we need to do that. Do we want to do a problem with grams and molecules? Yes? Okay, let's do a problem with grams and molecules. So here we have a question, and this is on page 29. Identify the known and unknown, and then we're going to map the problem. Okay. So I'm going to grab this so it's not quite so obvious. There we go. Oh, so big. How many NH3 molecules can be created from 8 grams of N2 according to the following reaction? So our known and our unknown. So we want to make our way from 8.0 grams of N2 all the way to NH3 molecules. So actually, do I have that? Alrighty. So I would like you to tell your partner in step 1, what will we convert into? What unit should we end up with in step 1? Tell your partner. Step 1 is always convert to moles. And moles of what? Moles of A. Who is A? N2. So we're looking, we want to convert to moles of N2. Step number 2, we want to convert to moles of, and who is B? NH3, because that's where we want to get to. So we want to find the moles of NH3. And then finally we can convert to NH3 molecules. I would like you to tell your partner what the conversion factors are for step 1, step 2, and step 3. What are those 3 conversion factors? And feel free to look on that new sheet that you got if you cannot remember. Step 1 is molar mass. Where does that come from? Periodic table. Step number 2 is the mole ratio. Where does that come from? Coefficients. And finally, moles to molecules, Avogadro's number, okay? So molar mass is grams per mole. All right, let's do this conversion. We have 8.0 grams of N2. We want to use the molar mass of N2. We need to cancel the grams, so grams go on the bottom. Find the moles, so moles go on the top. Nitrogen has a molar mass of 14. There are 2 of them, so it is 28.0. Oops, what did I forget? Of N2, because I'm going to have to switch, right? So I need to have moles of whatever it is. So now moles of N2 go on the bottom, and moles of NH3 go on the top. And I go up to my question here. N2 has a 1, NH3 has a 2, N2 has a 1, NH3 has a 2. And finally, we want to end up with NH3 molecules, so let's put those on the top. And we want to cancel moles of NH3. The 1 goes with the mole, and then 6.02 times 10 to the 23 molecules goes on the top. Okay, and I think the calculation is done for us. over here. Oh, no, we didn't actually do the calculation. We were just mapping it. Okay, cool. Do you need another example like that? No? Okay. For the next 3 examples, identify the conversion factors used in each step. So this is on page 29. Example 1, we want to know what is the conversion factor here and here. Tell your partner. You can use MR for mole ratio, MM for molar mass, and AN for Avogadro's number. We're going to go really fast. We're not going to do all of it. We're not going to get through like percent purity or anything like that, or even percent yield. No. Next Tuesday. Yeah. No, don't be stressed. Oh. Right. It's okay. If it doesn't work out, we'll sort something. Okay? All right. For this first one here, what's the conversion factor? Particles to moles. Avogadro's number. Moles to moles. Mole ratio. Grams to moles. Molar mass. Moles to moles. Mole ratio. Moles to molecules. Avogadro's number. Atoms to moles. Avogadro's number. As long as it's some type of particle, it doesn't matter if it's atoms or molecules. And then moles to moles, mole ratio, and then moles to grams, molar mass. Okay. I don't want to do these problems, so we're not going to do them right now because, quite frankly, I would like to cover gas stoichiometry, which is on page 33, because we are really trying to get through at least to limiting reactants. We won't get to percent yield, but I really want to cover limiting reactants with you guys tomorrow. So gas stoichiometry, a handy shortcut. The volume ratio, guess what? What is the volume ratio the same as? Ha, 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 ha. It's the same as the mole ratio because equal numbers of moles occupy equal amounts of space. Yes? Because if we have 22.4 liters of NH3, let's zoom in there. 22.4 liters of NH3, let's assume we are at STP. How many moles is that? Uh-oh. How much is 22.4 liters of a gas at STP? How many moles? 1 mole. So that's 1 mole of N2. And you can see we have 1 volume. Like I've put a little box around it. That box represents 1 volume. Yes? Now, 67.2 2 liters of H2. How many moles is that? 67.2 divided by 22.4 is 3. So here we have 3 moles of H2. And guess what? How many volumes do we have? We have one volume, 2 volumes, 3 volumes, 1 volume. When we react, hi. All right, and then finally we get, if we react 1 volume of N2 with 3 volumes of H2, we will get 2 volumes, 1 volume, 2 volumes, and that is 44.8 liters of NH3. How many moles is that? 2 moles of NH3. See how we have a 1 to 3 to 2 mole ratio, but we also have a 1 volume to 3 volume to 2 volume ratio. You don't actually ever have to use the volume ratio. If you want to keep going, convert to moles first, and then convert to moles, and then convert to liters. So if you wanted to go liters to moles to moles to liters, you could do that. But if you just want to go from liters to liters in one step, rather than 1, 2, 3 steps, you can do that. Okay? So let's take a look if we have a question like this. How many liters of NH3, actually let's do this. How many liters of NH3 are produced when 0.5 liters of N2 are reacted with lots of H2 at STP? And we have our reaction, of course, is N2 plus H2 gives NH3. We've got a 3 and a 2 for our hydrogen, so that's a 2 and a 3. And oh, that's balanced now. Excellent. So let's map this problem. We are starting with 0.50 liters of N2. What do we want to finish with? Liters of NH3. Now, if we're following our stoichiometry rules, step number 1 is to convert to moles. Moles of what? N2. And then step 2 is to convert to moles of the second thing, which is NH3. And then finally convert from moles to liters. Now, I would like you to tell your partners what are the conversion factors for each of these steps. Step number 1, step number 2, step number 3. And feel free to refer to that sheet that I just gave you today if you can't remember. And these are gases at STP. Okay, so in step number 1, I've heard people say molar volume. If you know it by that name, that's great. But if you just want to say 22.4 liters per mole, you can also just say that. Okay, it's short enough that you could write that down on its own. Okay? Oh, liters per liter, that's fantastic. Liters per mole, thank you. Okay, what's step number 2? Moles of one thing to moles of the other thing. That's the mole ratio. Where does that come from? Coefficients. And moles to liters, these again are gases at STP. Moles and liters would be molar volume, which is 22.4 liters per mole. And I want you to take note of the fact that we have this conversion factor not once, but twice. Let's see what that looks like. Okay. So in step number 1, we put 22.4 liters on the bottom so that will cancel liters of N2. Okay, then we have our mole ratio, which is useful, right? But guess what we have next? We have 22.4 liters per mole. So we end up dividing by 22.4 and multiplying by 22.4, which gives us 1 liter of NH3. If you want, you can do it that way, no problem. If it's less confusing for you to do that, I go to moles, I go to moles, I go to my final thing, that's great. But if you want to save yourself a little bit of work, you can use the volume ratio, which is the same as the mole ratio. Okay, you can say 0.5 liters of N2 times 2 liters of NH3 for every 1 liter of N2. This only works when you're converting from liters to liters of a gas at actually at any temperature and pressure, but we're going to say gas at STP because we're in grade 11 and that'll make it easier for you. Okay? Take care not to mix up volume of gas and volume of a solution. So this is on page 34. Page 34. Where'd it go? Okay, let's map this problem. What is our known substance here? Tell your partner, who is the known and who is the unknown? Tell your partner, who's the known? Who's the unknown? Okay, it's pretty obvious what our unknown is, yes? Volume of CO2, and I want you to take note that that is a gas. So we want how many liters of CO2? Okay, so that is our unknown. So that is substance A or B. Our unknown is substance B. And that means that our known is the HCl. When you see molar, what does that tell you about the state of the HCl? That tells you that it is aqueous. Can you use 22.4 liters per mole for an aqueous substance? No. Okay, not for aqueous. This, however, is a gas, so we say yes, 22.4 liters per mole. Okay, so you do have to look at your states and say, what am I dealing with? Can I use 22.4 liters per mole only for gases? Let's map this problem here. I'm going to give you a choice here. We have 1.25 liters of HCl, and we have 0.0055. What should I do with this unit here? Molar. Moles of HCl per liter. One of these is the initial quantity and one is a conversion factor. Tell your partner which one is the initial quantity and which is the conversion factor. $1.25 liters, initial or conversion factor. That's our initial quantity. Because the conversion factor has 2 units that allows you to convert. Okay, this is our conversion factor. So we are going to be starting with, here's our map, 1.25 liters of HCl. And eventually we want to end up with liters of CO2 gas. What will we be converting 1.25 liters of HCl into? Tell your partner what's step number 1. We convert to, always convert to moles. Moles of what? HCl. What's step number 2? Moles to moles. What's B? CO2. So we're going to find the moles of CO2. Okay, and then in step 3, we'll find the liters of CO2. I would like you to tell your partner what conversion factors we're going to use here, here, and here. And remember, HCl is aqueous. What's the conversion for step number 1? Molarity. Moles per liter. Molarity. What's the conversion from moles to moles? Mole ratio. And what is from moles to liters when we have a gas? 22.4 liters per mole. So what I'm going to suggest to you is when you see liters, you make sure you write down if it's aqueous or if it is gas. Okay, so when you're actually writing it down and you're making your map, or even if you're just, doing it as in a conversion string, write down whether it's aqueous or a gas, and that will help you not use the wrong conversion factor. Okay? And we would do this calculation. We have our moles per liter, there's our concentration, molarity, there's our mole ratio from the balanced equation, and there's our 22.4 liters per mole, and we get that. Whenever you are asked or given a volume, be sure to check if it is a solution or a gas, and even better, write down. If it is a solution or gas. All right. So, with those tools in your toolbox, we can now do let's see, pages Why don't you do page 31? And page 35, 36. Okay. That's 9 questions in total. Sound reasonable? Okay. No, this is it. We're done for today. No, we're not done everything. We still need to do limiting reactant. We're going to learn that tomorrow after the quiz. The quiz tomorrow is on enthalpy. So if you wanted to do any of the enthalpy stuff in Hebden, you could. Okay, so our quiz. Yes, sorry. 4 and 5 is wrong? Okay. The answer key for 4 and 5 is wrong, but it is correct is it correct in here? It's correct in the answer key, but it's wrong at the bottom of the page. Okay, so 35, page 30, is that page 36? Yeah. Page 36. Number 4, 5. The key at the bottom of the page is wrong. But the answer key is correct. Because the worked answers are in the answer key. Okay. And for your enthalpy quiz, there is stuff on Teams. I think it tells you the Hebden pages as well if you're interested in the Hebden pages. Okay.